problem by partitioning the problem into sub-problems. We already learned a technique to solve a problem by partitioning. What was it? Park Jong-hun? What was the technique? So we learned a technique that solves a problem by partitioning the problem into sub-problems. So what was the name of the technique? Divide and conquer. Yes, divide and conquer. Dynamic programming is another way to solve the problem by partitioning. But there are differences. In the case of divide and conquer method, the sub-problems are independent, like this. But in the case of dynamic programming, the sub-problems are not independent. That is, to solve this problem, these three sub-problems are used. And these two sub-problems are also used to solve this problem. So that is the main difference. So a dynamic programming algorithm solves every sub-problem just once and saves its answer in a table and then reuse it. This is the main point, and I will explain using an example. Dynamic programming is used to solve optimization problems. A brief outline of optimization problems is like this. First, there are many possible solutions, and each solution has a value. And we find a solution with the optimal value. The optimal means maximum or minimum. And such a solution is called an optimal solution to the problem. Look at these articles. There is only one optimal value, so it is called the optimal value. But there can be many optimal solutions with that value. So we say an optimal solution. The shortest path problem is a simple example. Look at this. This is the source vertex, and this is the destination. And then the shortest path problem is to find the lowest weight path or lowest cost path from the source to the destination. And look at this. Okay, let me draw another line. How many paths are there from the source to destination? 박근배. The number of paths, not the shortest paths. Three paths, right. There are 1, 2, 3 paths. So there can be many possible solutions, means there can be many paths. And then each solution has a value. In this case, the path weight is a value. What is the path weight of this path? It's 3. How about this? It's 3. It's 5. Yes. Every solution has a value. And we find a solution with the optimal value. In this case, shortest means the minimum. Yes, what is the minimum? 3. Yes, in this case, 3 is the optimal value. And there are several solutions having that value. How many solutions are there? 2 solutions. 1 solution and 2 solutions. Okay, so we know that there is only one optimal value, but there are several solutions satisfying that. Okay? And developing dynamic programming algorithms can be divided into 4 steps. In the first step, we characterize the structure of an optimal solution, and then recursively define the value of an optimal solution. Then compute the value of an optimal solution in a bottom-up fashion. And finally, construct an optimal solution from computed information. Okay, it looks quite unfamiliar. Let me explain this throughout this class using an example. And the example is assembly line schedule. Okay, let's see. Assembly line is like a conveyor belt in a car assembly line. Look at this. In this case, there are n stations. Each station assembles some parts. In some station, workers attach doors to a chassis. And in some station, they paint. In some station, they assemble steering wheels. So, okay? And we denote each station by SI. And then AI means assembly time in the ICE station. So station 1 takes A1 time, station 2 takes A2 time. And this time is entry time. That is to put a chassis into the conveyor belt. And this is the exit time, to take the completed car out of the assembly line. So the problem is determine the fastest assembly time. In this case, it isn't difficult because there is only one assembly line, so we just add all the times in this assembly line. Okay? It's simple. We have, and let me add one by one. In this case, we have 2 assembly lines. So each station has 2 subscripts. First subscript indicate the assembly line. So this is assembly line 1 and this is assembly line 2. And the second subscript is the station number. And AI is also denoted in the same way. Okay. Then let's consider the example, the problem. How can you compute the fastest assembly time in this case? This is a simpler problem. There is no change between assembly lines. Yes, it's simple. We add all the times in the first assembly line and all the times in the second assembly line, and then we compare and take the smaller one. Okay? That is the question you already answered. Then assume that we can switch assembly lines after each station. Assume that in each column, 2 stations have the same function. They do the same thing. So we can switch to the assembly line 1 after second station. Then how can we find the fastest assembly time? And you already answered. What was it? Yes. We take smaller. In this case, we have to add these 2 terms because they are in a chunk. So compare these 2 values and we take the smaller one. And then take the smaller between these 2 stations and do the same way. By taking the minimum assembly time in the same station, we can find the fastest assembly time. It is not difficult until now, but this makes this problem harder. There is a transfer time. T11 is the transfer time to take a semi-assembled product to this assembly line. Then this problem isn't easy. Okay, then can you find an algorithm to solve this? I'll give you a few minutes and try to find a way to solve this problem. Even though it is inefficient, at least find the answer. Okay, then think of a brute force or straightforward method to solve this. Let me explain. First, let's think about the brute force approach. That is, we enumerate all possible ways and find a fastest way. There are 2 to the n possible ways. Why? Can you explain? 최소리, 김종빈. There are 2 to the n possible ways. Can you explain why? Yes. In each column, we can take one of 2 stations. So 2 possibilities, 2 possibilities. So there are n 2 possibilities. So the number of paths is 2 to the n. Too many paths. What is the running time? For each path, we have to add all the values, and it takes big O of n time. So the running time is n times 2 to the n. It's exponential. So we have to find a better way. And the first thing is, let's observe this problem structure carefully and find out the optimal substructure. As this is important. This means an optimal solution to a problem contains an optimal solution to subproblems. That is, look at this. Assume that the path U to V through W is a shortest path. Okay? This P1 and P2, if they are concatenated, it is a path from a shortest path from U to V. It's fact. Then this becomes a shortest path from U to W, and P2 becomes the shortest path from W to V. That is the optimal substructure. Is it true? Can you show it? 신경실. Can you explain why this is true? If P is a shortest path, then P1 and P2 are shortest paths. 어미송.
P1이나 P2가 제일 짧은 길이 아니면 제일 짧은 길이 존재하니까 그걸 더한 거랑 다른 거죠. 그러니까 P1이 만약에 짧은 게 아니면은 P1 말고 U에서 W로
P1 prime.
네, 짧은 길이 존재하니까 그거랑 P2를 더한 게 P1과 P2를 더한 것보다 작으니까 안 되지 않죠?
Yes. We can show it by contradiction. Assume that P1 isn't a shortest path. Then there is a shorter path, P1 prime, from U to W, P1 prime. Then P1 prime and P2 is another path from U to V. And it is shorter than P. So it contradicts the fact that P is a shortest path. So both P1 and P2 are shortest paths. And this is true for all subpaths of P. That is the optimal substructure. We can use this fact in our problem. That is, the fastest way to S14 contains the fastest way through either S13 or S23. That is, the fastest way to this station is either the fastest way to this station and this edge, or the fastest path to this station and this edge. Okay? So we can use this fact to solve this problem. The second step is a recursive solution. let f sub ij denotes the fastest time to finish station Sij. That is, F14 is the fastest time to finish the fourth station in line 1, and F23 is the fastest time to finish the station 3 in line 2. And F star denotes the fastest time to finish all stations. Then we can draw these recurrence. Okay? I'll give you a couple of minutes and then try to understand this pseudocode. This is the jth column. So we already assume that we already computed the j minus 1 column, j minus first column. Then using these values, this is the station in assembly line 1. So if the semi-assembled car is from the same station, same assembly line, we just add the working time at the station J. But it is from the other line, we have to add the transfer time from the other station. And this is symmetry. This is the case when the station is in the assembly line 2. Then if the semi-assembled car is in assembly line 2, we only add the assembly time. Or it is from assembly line 1, we have to add the transfer time. The final result. So if it is from the assembly line 1, the time to finish the last station in assembly line 1 plus the exit time of 1. And in assembly line 2, finish time plus the exit time of 2. Yeah, then it's time to compute this. Actually, this is recursive. It is recursive. So we can use recursion to solve this. But if we use a simple recursion, the running time is theta of 2 to the n. Why? First, we call two recursive calls. One is on this, and the other is on this. And to solve this problem, we call two calls recursively to these two stations, right? But when we solve the problem on this station, we also call recursively on these two stations. So this problem is solved twice, and this problem is solved also twice. Okay? Then this column, on this column, each station is called 4 times. And then 8 times, 16 times. So we solve these two problems to the n minus 1 times. So that's why the running time is long if we solve this problem recursively. And the reason is that same problem is solved multiple times, which is really redundant, unnecessary. Okay? So, how can it handle this problem? That is, instead of solve the problem recursively, we solve them in a bottom-up fashion. And then we store the result in the memory space. Look at this. Okay. So in this case, the entry time is 2 and 4, and each value in each station is its assembly time. And let's see. So it's 9. There is no other choice. And it's 12. There is no other choice. And then we consider, and now we are computing this. And it is 9 plus 9, which is 18. And there is another pass from the other line. That is 12 plus 2, which is, 12 plus 2 plus 9, which is 23. Then 18 is smaller, so we take 18. So we compute the values from the earlier stations and later stations, then later stations. And how about this? 12 plus 5 is 17, and 9 plus 2 plus 5 is 16. In this case, 16 is smaller. So we took 16. And then this. 18 plus 3 is 21. 16, 1, 3, which is 20. So 20 is smaller. And this. 16 plus 6 is 22. And 18 plus 1 plus 6 is 25. So it is 22. In a similar way, we can compute all the finish times at each station. Finally, okay, this is the finish time of assembly line 1, which is 35. And 37 is the finish time of assembly line 2. And we compute the exit, we consider the exit times, and this is faster. Okay. And the running time is just theta of n. Why? We have 2n stations, okay? The number of stations is 2n. And to compute a finish time in each station, it takes just constant time. We have several additions and comparison, and one comparison. So the total running time is theta of n. So it's very, very smaller than the theta of 2 to the n, which is a recursive solution. Okay, then F star is the fastest assembly time But we want to know, this is the optimal value. This is not solution. We want to find the shortest path, the fastest path in this assembly line. Then we have to do more like this. We need to store another array, L array. This is the F array, okay? We maintain an array F, and instead of writing an F array like this, I indicate every entry in each station. To construct the fastest way through this factory, we need to maintain another array. It is called L in this textbook. That is, look at this. It is from 2 to 6. And we have 2 rows. This row is for the assembly line 1, and this row is for the assembly line 2. And there is an L star. L star means finally, when we compute F star, we took this. That is the result from assembly line 1. So L star is 1. So this is the assembly line number. Where does it come from? And look at this. In this case, the result is from the assembly line 2. So we wrote it in the L table. We wrote 2 here to indicate that the result is from the assembly line 2. With this array, we can trace back to this station. And then we use line 2 and station 5 to find out where is it from. It is from assembly line 2. And then assembly line 1. Then 2, 1. Okay. Note that this information doesn't exist after the computation of the F table. F table stores only the boxed values. They don't store where is it from. The origin information is stored in table L. When we compare the values, its previous values, and then we take the smaller one. Then we store where is the smaller value from. Where the smaller value is from, we store it. Without that information, it isn't easy to find this path. Okay, then let's consider the space consumption. Table F requires 2 to the n entries. Why? in assembly line 1, there are n stations. And there are other n stations in assembly line 2. So there are 2 n stations in total. And we have an entry for each station. We have an entry of F to each station. So that's why table F has 2n entries. So actually these boxed value, including this, are stored in F. And then table L has 2n minus 2 values. Why? 임하경. Yes, we don't store L values for these first 2 stations. Look at this. We don't have to. They are from only here. So that's why table L stores, table L has only 2n minus 2 values. Okay, then we have quiz like this. We can reduce the number of entries in table F from 2n to 4. When you compute these 2 values, we only require the previous column. We don't have to store all the previous columns except the column right before. So we need only 4 entries. The previous 2 values and the current 2 values. Okay? All the other values are obsolete, and we don't need them. So this is one way of reducing space. Okay, then the other way is, this way is to reduce table F. Or if we don't reduce table F, we can abandon table L. We don't need table L. Without table L, we can trace back. In constant time, yes, right. Without the value of L, the table L, we can trace back like this. We don't store 36, but we already stored 32 and 30. So we can calculate again. From 32, it is 36. From 30, it is 35. Then we can trace back to this line because its value is smaller than this value. But we cannot abandon both of them. We can reduce only one of them, either F or L, but not both. I think we need 3 exams. 1 exam, and I think around this time we will have another quiz. October 13th. Sorry. Yes, not October. November 13th. I think we can learn dynamic programming and greedy method. Then using only those parts, we can have another quiz. But it is not fixed. It may, so about this data. Okay, then wrap up this class now and have a good weekend. See you next week.